Okay, good afternoon. I have a long list of things to tell you. Welcome, first of all, to the third fall 2009 Nokia Distinguished Lectures on Cyber-Physical Systems. The series of lectures is organized under the umbrella of CITRIS, the Center for Information Technology Research in the Interest of Society, and CCIT, the California Center for Innovative Transportation. This lecture is organized by the Intelligent Infrastructure Cluster at CITRIS. The lecture is also broadcasted live on the other CITRIS campuses, actually, in particular Davis, Santa Cruz, and Merced, and will be on the web on YouTube after the talk. If you are watching also online, you can email us your question, which will be read at the end of the lecture. Let me say a few words about the Nokia Distinguished Lectures series on cyber-physical system. As indicated by the title, the lecture series focuses on the application of novel technologies which integrate computation and physical systems. A good illustration of this is the current Nokia Berkeley project called Mobile Millennium, which is the origin of the genesis of this lecture series. And you can find more information on the website traffic.berkeley.edu. Today's lectures will be held by Professor Manfred Morari, and probably most of you know Manfred. He, since 1994, has been has been head of the Automatic Control Lab in Zurich, ETH, Swiss Federal Institute of Technology. Before that, he was a professor and the executive officer of the Control and Dynamical Systems at California Institute of Technology. He is a recipient of a numerous number of awards, and not list them all. In the control field, the Ekman Award, the Ragazzini Award, and the IEEE Control System Field Award. And in the chemical field, there is numerous numbers of awards. I don't even know them. He's also, I learned that he's a member of National Academy. He's one of the youngest members of National Academy of Engineering of US. He was elected when he was 42, around 42. And today he's going to talk about control of energy management systems. Thank you again. We look forward to your seminar. I guess we don't have to use this.
Thank you very much, Francesco, and thank you for coming. Good afternoon. I enjoyed this 15 minutes late. You know, that was the Austrian custom that in Switzerland I had to forget. When I once was 10 minutes late, I was criticized heavily, and so but that's back to Austria. We have this academic quarter hour, which comes to application here. What I would like to talk to you about today is about some work that is going on at our laboratory, at the Automatic Control Laboratory, as Francesco mentioned. We have several projects that are in this general area of energy management systems. And I think that they can demonstrate very nicely this interplay between the physical and the information structure, and modern control algorithms can take advantage effectively of this interplay. The talk today will be very much application focused. Let me first give you some context and motivation for what's going to follow. Energy producers, energy consumers are distributed. Consumers, we know, producers increasingly so with the increase in alternative energy sources. And the current practice, at least referring to the examples in the seminar, is to have larger local control strategies. And the future goal would be to coordinate those strategies in order to optimize cost, efficiency, environmental impact, and comfort. And the tool that you will see being used is this technique, model predictive control, that I talked about when I gave this series of seminars here last year. And I will briefly summarize that and then talk about two applications that we are involved in. Both are projects in progress, not completed. One has to do with hydroelectric power, and the other with building energy management. And in both cases, we'll see how we can apply model predictive control. So first, let me give you a short outline of model predictive control. You have on top this slide showing, I think it's an automatic transmission. Classical control would be what you learn typically in your undergraduate control course, some transfer function or something like this K of S that represents the controller. But what you would do now, and what I will talk about, is replacing this controller K of S with something much more elaborate and complicated and sophisticated, and I just call it optimizer here. The idea behind this optimizer is that you will solve a so-called receding horizon control problem. Means, for example, you would like your system to follow some trajectory indicated by that line here. Then you will formulate a problem in order to calculate the manipulated variables over some future horizon such that your predicted system trajectory follows as closely as possible, defined by some metric, the required set point. And obviously, disturbances may happen, model predictions may be inaccurate, and so the idea is that you apply only the first one of those pre-calculated moves and then take another measurement of the situation of the system at the next time step, and then they repeat the whole optimization at the next time step. Now, formulating it somewhat more rigorously, we can formulate a performance index that I assumed here to be some P norm of a weighted state and weighted input over some horizon n. And the objective that we minimize online is that we find the sequence of control actions U over this horizon, as I indicated on the previous slide, such that we minimize this objective subject to model information, subject to constraints. And so looking at the block diagram, again, similar to what I presented before, we have this optimization problem. We figure out the sequence of future control moves. We implement only the first one on the plant, retake information from the plant, new measurement, and then redo the optimization problem. Now, almost 10 years ago, was realized that you actually can pre-compute rather efficiently, at least for a small system, the solution of this optimization problem. So instead of solving the optimization problem online for each measured plant state, you just pre-compute the solution for a set of plant states that you are likely going to visit. And this is then called a parametric optimization problem. And so instead of solving it online, you're computing a lookup table effectively that has the solution of this optimization problem. So you have here the state, you have here the control action explicitly given. And so online, all you need to do is use this lookup table. And that was around 2000, where by different groups, Norway, Australia, and in Switzerland, that was more or less discovered simultaneously. That you can do it in principle is clear, that you can do it actually numerically for a reasonably sized practical system was not obvious at that time. What's interesting is looking back, I just came from a workshop in Pavia on nonlinear model predictive control last weekend, and 10 years ago there was the first workshop. 10 years ago, the whole workshop was focused on process control and chemical engineering problems. Now, that workshop, 10 years later, on this nonlinear model predictive control, process control essentially had disappeared, okay, and was focusing almost exclusively on a wide range of other areas. And why? One reason is undoubtedly this explicit computation, improved computational resources in general, that allow now to take that somewhat more complicated approach to control computation to a whole new group of applications. in terms of properties, clearly, if I calculate now this control law explicitly as I indicated, or implicitly doing this nonlinear optimization, I get the same control action, and so the properties carry over from the online optimization to the explicit control law, and they have been studied extensively in the literature over the last 2 decades, and very strong results are available on how to choose the controller parameters, how to formulate the optimal control problem such that this receding horizon property guarantees stability, guarantees satisfaction of the constraints, etc. And I would claim it's actually the only tool that is applicable that broadly that gives you those type of guarantees. Depending on the model that you use and depending on the objective function, you get different types of optimization problems. Most commonly, and what was the original formulation, is that you just have a linear system plus constraints, and then this optimization problem, which you would have to solve online to obtain your control action, will be either a linear program or a quadratic program, depending on the objective function. And in the next step of complexity, if that linear system is not constant but a switched linear system, then the resulting optimization problem would be a mixed integer linear program or a mixed integer quadratic program, again, depending on the objective function. A lot of other extensions were studied with nonlinear models, how to account for uncertainty, and depending on that formulation, you get more complex optimization problems that in general need to be then tailored to that particular structure of the problem in order to allow an online solution or even offline solution in the time that is sampling time that is available. So that's the background. So what I want to do now is go into the first one of those 2 application areas and show you how those problems in those areas are handled traditionally and how they are now handled or will be handled, or the intention is to handle them within that new framework of model predictive control. So this first project is a collaboration that's going on and is financed by E.ON. So that's the big energy company. And there are 2 smaller companies, Wittmeyer, that makes control systems, and Cytec, which is a consulting company, especially for hydroelectric, in the hydroelectric power sector. So how important is hydro? If you look at, in terms of global electricity generation, about 2/3 of the electricity globally come from fossil sources, and the rest of it, half of it comes from hydro and half of it from nuclear, okay? And then there's a little bit new renewables, meaning not water, but solar and wind, etc. And in hydro, you distinguish 2. You have some storage hydro plants, like indicated here, or you have the river hydro plants, and that will be actually the type of hydro plant that we are focusing on in our work. Now, looking at Switzerland, obviously small country, small consumption, but Switzerland is very green in the sense that roughly half the electricity comes from hydro and half of it comes from nuclear. There's no fossil power. I say roughly because there's the rumor that some odd accounting is going on in the sense that one buys electricity from nuclear plants and stores it in hydro, pumps water up and stores it there and then sells it as green power the next day. Okay, but that's roughly it's 50-50. In terms of the distribution between the power plants, you have about half run-of-river and half storage power plants, and then you have a small percentage of hydro power plants that are used for energy storage. And we had a big discussion just 2 days ago in terms of energy storage, and turns out that that is still assuming that you have the space and the water, etc. available, that is one of the most effective ways of electricity storage. It's about 75% effective, meaning you get the electricity, run the pump, pump it up, get it down, regenerate the electricity, you have about 25% loss. So, and that is hard to beat with other technologies, at least at present. So, let me give you the problem definition. Here, power plant aerial view. Sorry, river aerial view. The power plant actually is this little thing here. This is the route of the river that is used for shipping, and you have some locks at this location. And taking a more closer look, that is a structure. So you have usually a situation where you have the power plant and locks that bypass the power plant. You have some inflow. You have some what's called the concession level, where you have to maintain a certain level of the river. And here, the manipulated variable, meaning how much water do you allow go through the power plant for electricity production. As disturbances, you have inflow from upstream on one hand, and second, operation of the lock that disturbs the flow of the river that you have to also account for when you try to operate those turbines to keep the level at the required point. Now, the challenge comes when you have a cascade, another single power plant, which is indicated here. The variables stay the same. The cascade offers also the challenge of having inflows from the side, that you have those disturbances from the locks, and that you have to, in principle, coordinate those tasks between the different power plants. Now, what's the objective at the minimum? It is that you want to keep those concession levels by within a certain range, that you don't want to change the turbine flow very frequently, and you want to respect the concession level, as I said, and you have also some absolute constraints on the turbine discharges. Now, there are other objectives that we have not considered at this point, but which can be important in certain situations, and that would be actually maximizing or optimizing the economics as the driving objective when you operate those power plants. What's the idea? The idea is that in general, you will charge more for the electricity at peak periods than, for example, at night. And so you could think about storing the river flow in those pools at night and then generating the electricity during the peak price period during the day. And obviously you want to do all that while obeying the limits that you're allowed in your operation. So there's this link in economics, which in this particular site where we are studying this is not possible or not relevant because you don't have enough capacity to do that storage. But I heard that there are facilities in France where that would be attractive. So control strategy, what's done traditionally, they have some simple local control strategies. They have a big operator console that looks over the whole river where the operators inspect the behavior of those local control strategies. They check if everything is okay, and if they don't see that there's some likely wrong behavior, they step in and they do some overriding actions that correct the local control action. So it's rather primitive what is done at present. And clearly what we would like to do is replace or at least substitute or assist the operators with a more advanced strategy where we use a model to predict the behavior of the river and then apply optimal, in the sense that I discussed, inputs in order to meet those concession level, optimize economics, etc. So let's talk a little bit about the modeling and the control. For the model, we use classic partial differential equation from Saint-Venant, dating back to the 1830s. that is the typical hydrology equation that is used. We have conservation of mass on one hand, conservation of momentum, so we get a first order partial differential equation, which gives us the flow as an input parameter, and which gives us the height of the river as a function of the location and the time. And that model is discretized in time and space in a standard manner, and gives us then in this form actually quite a high accuracy description of the behavior of the river, relatively high order. And the question that we will have to tackle, as I will mention later on, is that to look at somewhat simplified models, because we will get, as you will understand in a moment, very large optimization problems that can at present not be solved in the sampling time that is available. Here an indication of the model predictive control problem formulation. So it's rather standard. You have your constraints on the turbine action, on the change in the turbine, and you have constraints on the levers, and you can handle those with slack variables, where you put different weights on the slack variables depending on the range in which you allow this lever to vary. So up to now, with a linear model, linear constraints, quadratic objective function, you would have a QP, which would be very easy to handle. Unfortunately, there's some other constraints that the operating people rather insist on, and that is they want to enforce a dead band on the turbine discharge variations. That means they don't want to vary the turbine every 5 minutes by a tiny little increment, but they say we vary the turbine only once it prescribes a variation that is above or outside or bigger than a certain deadband range. Okay? And so in order to model this type of deadband, you need some integer model that integer variables that model this switch that you want to enforce. And don't want to go into those details here, but you can easily, for example, describe, as is shown here, this behavior that says basically delta U is either 0 when those two integer variables are both 0, then delta U would be greater or equal to 0, or delta U less or equal to 0, or it is outside the dead band, depending if variable 1 is 1 or variable 2 is 1. So you get those two integer variables for each time step over your horizon for each turbine that you are considering. And so you are now at the level of a mixed integer quadratic program, as indicated here, which we solve with standard software packages, Cplex. And the problem here is, especially because of this integer variable, or only because of this integer variable, that problem becomes computationally infeasible within the time period of the sampling time, which is 6 minutes, for larger number of plants, and that will indicate what larger is in our context. So in terms of case studies, at this point, simulation case studies, but the intent is that it will be implemented on the whole river. We have a very detailed model of the river with some simulator from the company Cytec that I mentioned. And we are studying the behavior for a range of inflow variations of the type indicated here. And I will not show you the many case studies that we have done, but just one or two that will indicate the behavior that can be achieved relative to the current strategies. So here's a behavior that emphasizes in particular to hold the concession levels constant. You can obviously go the other extreme, that you want to vary your turbine as little as possible. Okay, so those, and you can go through the whole continuum of strategies between those two extremes. So here are the details. So this is the inflow scenario, and in this particular simulation, 4 power plants are considered. 6-minute sampling time. You look into the future, 25 steps, so about 2.5 hours. You have various ranges in which you want to keep that concession level. So this would be a traditional strategy. What's given here is the concession level as a function of time in response to the disturbance input with a traditional PI controller, and then the improvement that you get with this model predictive controller indicated here. Now, when one sees something like that, the first response, okay, that would probably need very aggressive action of the manipulated variable in order to achieve that behavior relative to the PI behavior. But it turns out here the manipulated variable action, meaning the turbine discharges, again for the 4-power plant with the traditional PI controller, and then compared to the now model predictive controller, you see actually that the differences between the two control actions are very little. So it means with a better and more intelligent control action, you get vastly improved control without more aggressive control action as you would usually expect. So in terms of conclusions and outlook, models, as we said, standard based on those linearized Sand-Venant equations. MPC is well suited for that example. Tuning is straightforward. State estimation is required, but also rather straightforward. Sorry, I skipped here. Now, what's the outlook? The outlook is from the currently 4 to go to 35 power plants. That is a river in Germany. Actually, there's no river in Switzerland where we have 35 power plants. And not only that, Switzerland is so fragmented in terms of the power industry that you don't have even a situation where there are more 4 power plants in a row owned by the same company. Okay, and if it's owned by different companies, then they don't talk to each other, and so again, the strategy that requires coordination is not feasible. But then in Germany, they have very big setups, so this goes over a length of about 350 kilometers. And there, the strategy that we are investigating now is some type of decentralized MPC strategy, where we would have some local controllers with some coordination between the subsystems. The coordination depending on the need, so it could be a coordination, for example, in this case, probably only downstream, where you would forward the predicted turbine discharges from one power plant to the other to achieve that type of coordination. So this is the outlook. I should mention, and I will not dwell on this, there are a number of references, also what other people have done. The problem has been studied, for example, also in the context of irrigation channels, where the objectives are somewhat different, but the problem is similar. So that, as I said, is ongoing, and the objective is that next year that should be implemented by E.ON in Germany on the 35 power plant system. So the second example that I want to look at is energy management systems, and in particular using weather forecasts in order to enhance comfort and to save energy. And this is a large collaborative project, and I will describe the partners in a moment. We'll start with some data for motivation that I actually took out of a proposal that Berkeley was part of. So those are data for the US. Why are buildings important? Buildings are a major consumer of energy. Actually, if you divide the consumers into industry, buildings, and transportation, each one of those sectors takes about 1/3 of the total energy consumed in the US. Specifically, buildings take about 39% of the energy, 71% of the electricity consumed in the US and 54% of the natural gas. Major producer of carbon emissions. That means buildings are an extremely important consumer of energy and producer of carbon dioxide, and therefore should probably receive the primary attention in terms of improving energy efficiency and carbon emissions rather than cars, for example. Specifically also what is disturbing is it's the only energy sector that if you measure energy intensity, so for example miles per gallon, it's an energy sector that has increased the energy intensity. So it means over this period, 85 to 2000, the BTU per square foot has increased in the US. So it would be like the mileage has decreased, and further growth in this energy intensity is predicted. Now, I showed those numbers recently in a symposium in Switzerland, and I was immediately criticized because they said this is only an aberration of the United States. That is not the situation anywhere in Europe, where the energy intensity has actually improved significantly on this square foot basis. Now, in this proposal that was recently funded, Hyperbrick, where Berkeley Leisure Lab, as well as UCSB and other United Technologies are involved. The vision here is to come up with new strategies to enable a total transformation of the US commercial building sector over the next 2 decades. Okay? And the goals are very ambitious, as you can see here. 400 million tons of CO2 reduction annually, reduction in energy consumption, 90% in new buildings, etc. And obviously, if you see that, then you ask yourself, is this something you write for a proposal, or is this something you believe in? Okay? Is this something likely going to happen? Is it something like U.S. weaning the U.S. from fossil energy within 10 years? Is that equal to that? And actually, this is not unreasonable. Okay? I will now give you an example from Switzerland that there is a technology available that and can be implemented in this time frame if one puts the mind to it. Okay? Now, this example is not easily duplicated, okay, but it shows technology is there to do that. And it's a building that is actually a part of the ETH buildings. It's close to the ETH campus. It's for aquatic research. Just to give you a sense of the building, it's 10,000 square meters. That means 100,000 square feet roughly. Cost 33 million Swiss francs. Unfortunately, equal to the dollars now, essentially. Area, 150 people offices, lecture halls, seminar rooms, etc., book communication zones, and so on. Architecture, I think, is beautiful. Here you have the water molecule there as a main decoration here in the building. And now the data from the first energy audit. So those are not design numbers. Those are actually measured numbers, how much energy was consumed in that building. Just focusing on this. So this is a number of kilowatt hours per square meters annually. 14, if you're not in this area, that will not mean much to you, so I will put that on a relative basis. This would be primary energy demand, kilowatt hours per square meters annually for a usual new building in Switzerland. For a so-called min energy building, that's a new standard, min energy plus, and then this new building here that I was just describing. Okay? This is actually the energy amortized over the life of the building. That's for the construction of the building. Green is electricity, and the heating and cooling is just this part here. Okay? And if you compare it with standard, that's a reduction of more than a factor of 4 compared to standard building technology in Switzerland. So how was it done? Okay, what did they do to achieve that? And actually, no new technology was required. They just pushed the limit of what is technologically feasible at that time, and in particular combine the different elements in the systems approach in order to achieve that overall result. In particular, coordinate the building structure and the building services design. And this just as a background for what we want to do, so utilizing those weather forecasts. First, the project partners that are involved with us. It's led by an institute called Terrestrial Systems Ecology, our lab, the material testing lab of the ETH, then the Federal Office of Meteorology and Climatology, and Siemens Building Technology. Siemens, you probably know, mostly headquartered in Germany, but actually the Siemens Building Technology is headquartered in Switzerland because of some acquisition that went on. It's a 4-year project funded by various agencies, and we are here at the beginning. So the idea is obvious, okay? The idea is obvious in the sense that building dynamics tend to be slow. You know, this is an old building, a lot of thermal mass. You have new energy sources that tend to be intermittent, so let's say solar or wind or something like that. And so clearly it would be, most likely it would help to know what's going to happen with those sources when you control the climate in that building. And so the idea is you include those weather forecasts in the control strategy that you are proposing for the building. And I will show you just some preliminary first results on what you could possibly gain from doing so in particular situation. So weather forecasts, this is a shopping list of what we have available in Switzerland at least, from the simple, meaning simple extrapolation, tomorrow will be like today, to 3 different elaborate models that can give you deterministic or even ensemble forecast with some uncertainty information. And the models are different in the sense of how often per day they provide those data, over what time horizon, over what area, over the grid point, the mesh size that's available, etc. Now, obviously, at the end, we want to use the simplest that gets us the furthest. Okay? And that we will see what that is. I was actually also very surprised. Don't know if anybody's here from this area, but I expected that all those weather forecasts that you see on television are basically automatic. You know, you generate this and you give it to the people, but it's not the case. There's people interpreting, personal interpretation, and this is what you see. And actually, there's almost nothing that is immediately automatic. So there's some people filter in between. So at this point, we're looking at a small part of this whole building automation. We're looking at integrated room automation, and that means integrated control of the heating and cooling system, blinds, and lighting. Okay. Clearly, as I said, the idea is obvious. Question is, does it gain you anything? Okay. So before we get involved in developing elaborate controlled strategies, you want to find out what is what I call here the size of the prize. Okay, how much is potentially in it in such a control system? How much can you gain using weather forecasts? And so we did a massive set of case studies, different locations in Europe, weather input, occupancy input, and buildings orientation, different thermal insulation, different construction type, different window areas, etc. So sample from this 150 or so case studies, and I will just show you some numbers from those case studies. So this is should not be mistaken as what you can actually achieve. This is the maximum you can achieve. This is the ideal situation in the sense that you assume now the weather forecasts are perfect. Okay, you know exactly what's going to happen. You have a model of the building, etc. You have down here, the units don't matter for this discussion. You have down here the energy use that you would have with conventional control, and then how much the savings are in absolute terms relative to those numbers and relative savings here. And you see that at least for some of those scenarios, you can achieve quite significant savings, but you also see there's a significant spread. Okay, so some cases you can save almost nothing, some cases you can save a lot. So that means it's very situation dependent. If you analyze a little bit more, and this is again a glimpse at a large number of data, for example, distinguishing what's called passive housing and the Swiss average house, passive housing in green, and the Swiss average house. See, for example, large window area is good for those passive houses. Heavy building, large thermal mass is good in terms of in the sense of having a lot of potential for improvement of energy efficiency by utilizing weather forecasts. So this is summarized here. I emphasized here potential maximum savings from such an integrated room automation system, but it depends strongly on the particular situation. So it can be 30 to 40%, 60, even 70% in some cases. How can we get there? Okay, I gave you a target. I gave you a maximum achievable energy efficiency, but what do we have to do to get to that target? And that is looking at different control strategies. And that I want to give you a sense of what the control strategies will do in this context of building control using weather forecasts, using those diagrams, which are largely cartoons. So the idea here is you don't need in this room a perfect temperature of whatever it is, 68, 70 degrees. You need a temperature range. Okay? And you want to obey that temperature range most of the time, 90% of the time, etc. And so we have this comfort range, and we have here the violation of the comfort range. Now, if you don't care at all about the violation, then actually the energy that you need is zero. Okay? Just open the windows, comfort range is violated, you don't need the control, you don't need heating, you don't need cooling. Okay? As you want more comfort, as this violation gets smaller, you will pay more for it. If you want every day the room to be perfect, you pay a lot more than if you say 90% of the time the room is okay, otherwise it's a little bit too hot or too cold. And that's what's indicated by this trade-off curve. So you always have a trade-off between the energy you need, okay, and the comfort you have, or the violation of those comfort bounds as indicated here. And so, for example, a standard controller, as indicated here, will give you a particular trade-off curve. Now, what this target would do is something like this. Okay? It would give you a performance bound. And what does this performance bound mean? This means that down here, you have infeasible specifications. Basically, you want very high comfort, okay, little violation, for zero energy. So those are the infeasible specifications. And up here you have the feasible specifications. And then you have the degrees of freedom. So for example, you can reduce energy up to this point for a certain comfort range. So this would be the Pareto optimal curve, where you, along this curve, where you actually can only reduce energy by giving up comfort. Okay? But we are actually interested in reducing energy from somewhere up here without reducing comfort. So we want to shift that standard techniques over to the left, which gives you a better trade-off between any point in terms of energy efficiency plus comfort compared to the standard techniques. And so that would be, for example, using only weather forecasts but not uncertainty information. And so the next step would be using uncertainty information as well as the forecast. What's the idea? The idea is if the forecast is wrong, it will have a wrong climate control, poor comfort. Now, what we want to do is account for the forecast uncertainty. And that means so when the forecast is very uncertain, we'll do a cautious control and improve comfort. And that gives you this better improved trade-off curve as indicated by the red line. So that requires basically a stochastic optimal control strategy that gives you that good comfort as indicated by that red line here. And we have done some numerical work on developing methods that would be applicable also at this large scale problem as we would have it here, and I would be happy to discuss that in more detail in the questions. I have also slides to explain what we have adopted for this purpose. Now, some caveats, some warnings. What is standing between the ideal building that I showed you from Switzerland, between this optimistic control strategy that I present here and the real world? Okay, and the issues that stand here are non-technological, but they may be actually dominating what we can do in terms of realizing those energy savings. And I took this from a talk that was presented at the American Control Conference last year from Mr. Bushby from NIST. And there are two problems. One is already on the construction side and one is on the operation side. So when a building is constructed, and here indication is for a large commercial building, one general contractor that subcontracts it out to a number of other companies, and those cost pressures that come from the owner are passed down several levels to the subcontractor. So at the end, the only thing that counts is the costs at the moment for the building and not anything about life cycle performance for this system that is eventually installed. A big other issue is the commissioning after the control system is installed. That is either often done not well or sometimes not at all. As I emphasized, that was a presentation about the US. The person we work with at Siemens, Jörg Töttli, said in Europe it's exactly the same. So this is not any different from country to country. Now, once the system is installed, the second issue is operation. Operation, building maintenance staff poorly trained. The maintenance is done usually only when something is broken. And when it's broken, one introduces a fix, and that fix is then left in place even when it's not needed anymore. And so the original system can't do its job that it was designed for. If you need to save money on the building, then the first thing that's cut is facility budgets, and that's then has impact on the control and the energy performance. Just an anecdote, when I talked about this, actually the workshop that was organized by ABB, I was in a room, there were a set of vents, rows of vents to the building. One row was for air inlet, next to it was the row for the air outlet. Okay, so what would come in would be just sucked out next to it again. Okay, so clearly that's just an illustration of a problem that is mentioned by Mr. Bushby here in those slides. So in conclusions, in terms of this building climate control and building energy management, it's quite apparent that advances in information technology are enabling, in principle, major changes in building energy management. And the energy savings from control utilizing weather forecasts can be large, potentially, but it's very highly dependent on building location, orientation, etc. And therefore, our ultimate goal in this project is to develop an assessment tool where you enter all this information and it tells you what are the likely savings from what level of control sophistication. And the final point, maybe the most important point, though nothing that we do has any impact on that. That's a different group of people that are responsible for that. That the realization of those savings will require not only those technological advances that we are trying to achieve here, but changes in the processes that are now used for the implementation of the technology, for the operation and the maintenance of this technology. And with that, I want to close. Just here, picture at Siemens Building Technology of the team working on that. So I thank you for your attention. I would be happy to answer any questions. Thank you.
Questions?
Thanks. About the first presentation, the cascaded power plants on the river, how'd you get the models? How easy and expensive is it to get those models? How reliable are they? Do they change over time? You know, rivers silt up and all that, and so do you have to have adaptive models or whatever? Address all that?
Yes, a very, very good point. The Germans are relatively well organized, and you can get for this river that it's kind of ridiculous, but I'm not allowed to say the name. You can get those. They're in the public domain. They are and it's the reason is that there's intensive shipping going on. Okay, and so they need this information, even time varying to some extent, because they need to guarantee the possibility of the shipping and keep track of all problems of low water areas and all that. So in this, I think in situations where there is shipping ongoing, I think that information is available. I should also say that yeah, I can fill in afterwards. But that's here. But it is not. It is certainly not generally available, and it is again not easy because even after you get it, to then put it in the form, okay, is a major effort.
Commissioner. So on the modeling thing, since in your example you're keeping the concession variables to within very, very tight limits. You know, I think your number was 3 centimeters.
Yeah, more than necessary, actually.
Would you need to know the channel topography because you're keeping it? Okay, let's say 1 foot, 2 feet. You know, probably don't. Essentially, one out of linearized model.
Exactly. We use a linearized model. Okay, for the control, the simulation was done on the real model. Right. And that's what I wanted to fill in on the question that Phil had. I suspect that you can get by even simpler models than what we use here for that purpose. I think the important thing is the coordination, okay?
Correct.
But as you said correctly, first of all, if you keep it within those limits, but we also did sensitivity studies, like high flow, low flow, with the same unchanged detailed model. Performance was somewhat worse, but still quite good.
Second, you had a mixed integer quadratic program in the first part of the talk, and that came because of the dead zone constraint.
Exactly, only that.
Why not do a relaxation and and just implement the change only if?
Absolutely, there are many tricks that one can do. Relaxation, all types of relaxation that one can do. To get around this computational complexity that we are facing. One, I would say, obvious one that we have tried to some success is that one says, okay, it's important to take into account that deadband maybe 1 step ahead, 2 steps ahead, but 3 or 4 steps ahead, it's really not relevant for this long-term actions are not relevant for today, and so I can cut back. But at this point, that was still insufficient. Okay, so this was not enough to do this type of relaxation that I just described. Was not enough to get the complexity down for the 35 power plants to do it in 6 minutes. Okay,
No, yeah,
but there are various other things one can do.
Third question, and probably one that I really want you to answer. in MPC on the theoretical front, where do you see the opportunities?
Not much. Okay? So where I see the opportunities is computational. And that's I think, where the real issues are. So in the computation, I can give a whole list of problems that can be addressed. But we actually discussed it at this workshop that I mentioned. And I think the results that are available are very good, are very strong, are very nice. Clearly, you can do modifications to the available theory. You can always do some improvements. But I don't see the chance to do now a major new theoretical contribution there. Okay. One thing that would be, I think, if you look at theory, I think one thing that, let's say, the theory computational issue is that most of the strong results in the MPC area is how to formulate the problem such that stability invariance are guaranteed. Okay. Clearly, those are conservative conditions. They are sufficient conditions. And very often, our setups even don't use those conditions because they require long horizons and things like that. I think improving analysis techniques, okay, saying, okay, I choose that horizon, I don't choose the condition that a priori guarantees stability, but having a good analysis tool that then allows me to analyze over what range of operating conditions I maintain stability, I think that would be valuable. And I think there is definitely room for improvement, but it's tough. You know, it is tough because clearly what's done with this formulation, you know, you can think about those conditions that I mentioned, is they make the problem such that it's trivial to analyze. Okay? And so if you don't obey those conditions, you get general nonlinear stability analysis problem.
So regarding this, kind of like you show that this different manipulated variable, you get different type of the stability. The MPC one, that's very much stable on the reverse side, but then you have this PI one. So there are two questions here. One is actually if you do the shortest prediction, model prediction, so it's actually the same as PI, right? The shortest model predictive control. So it should be the same as PI. And actually, at least few papers actually published.
At least qualitatively, certainly it goes in that direction. I'm not sure it's identical, but certainly it should get characteristics that are similar to the PI.
Well, actually, there's a paper on 98 that we published that actually we've proven that these two pretty much the same.
But this paper doesn't consider constraints.
Right. That's a no constraint one. But the second one, the way I see it here, it looks like is a time delay is really the major issue in that one. And because you're manipulated, you can see that you have early prediction of the changes, and that's why you could actually make it stable. So you said also the computation here is that what is important. So if we actually have a shorter time for the measurement and then computation for optimization, so do you think actually that can be improved also?
I'm not sure that I totally understand. I mean, the problem was
for the
for
horizon that you're looking, and also the time steps is going to be shorter in a sense. Then you can actually have a smaller linear model rather than non-linear model.
I'm not sure that the time step is. I don't think there's need to reduce the time step. Okay, because. I think not much happens even within the time interval that we have now. The issue is more the time horizon over which we look. Now, clearly, you can simplify the computations by reducing the horizon, but that exactly, as I think you implied, gives you then problems with the performance. Okay, because in a way, you can imagine if you have a very long chain of those power plants, then it would be good to have this ability to predict what will happen from power plant 1 down to power plant 35. And that will require a kind of minimum length of horizon to take that into account, which the PI controller obviously does not do. And the PI controller, one can actually show, tends to even amplify the disturbances.
Right.
Okay, so because it is, you correct it locally, you correct for good behavior, but clearly what that means, you have maximum variation of the outflow in order to meet a local objective, which then is going to the next plant and again has maximum variations, and you can easily get an amplification of those disturbances as it goes to the chain. I think, as you said, because of the short-sighted tendency of a simplistic PI controller.
I wanted to ask this question about a theoretical scope of the research for MPC. So from PhD student point of view, I want to ask this question that so there are two issues for MPC. One is this constraint handling, and another thing is incorporating disturbances. Okay, so as regards to incorporating disturbances in modern process control systems, you have sensors and actuators communicating over like communication channels, right? So first thing is to how to actually model those constraints imposed by the communication channels inside this optimization framework. And second thing with respect to disturbances is this effect of this your weather prediction model as to how to actually realistically model the uncertainty, the stochastic uncertainty which is there. So
yes.
So do you think these two things are?
I think if I may start with the second one on the stochastic disturbance of the weather model, I was amazed, okay, that at least with the people that we interact with there in Switzerland on the Swiss Weather Service, they do not have a description of those uncertainty models. Okay, so they have no uncertainty model as we would want it typical for our stochastic control system design. So we are actually working with them to saying what we can use, what they can supply. We haven't converged yet in terms of uncertainty model that we can actually utilize and still do some computation on one hand, on the other hand, something that they can deliver. So I think that is a significant issue. Okay. Now, what is open at this point, I should say, however, is how much that uncertainty information will do for us is unclear at this point. Okay, and at least one thing we have already found from the computations that we have done, most of the uncertainty information is not important. The one factor that seems to be very important is the sun radiation. Okay, that is driving and dominating those improvements for those examples, etc. And so there we need this uncertainty information. The other thing with including the disturbance information, etc., yes, absolutely important. There have been all kind of works using invariant set theory in order to do that. The problem is most of it is limited to relatively simple low-order systems in terms of those computations. I think if one can improve that, I agree with you, that would be great. I think that's definitely would be an important factor.
Very quick question.
This a quick question. Have you tried to solve the MPC problem, the optimization problem, using, for instance, global optimization algorithms or other kind of techniques, like support vector machines, to solve the predictive task?
In terms of global optimization techniques, I mean, what we have here, let's say LP, QP, okay, you have global optimization, okay? If you do MI, LP, at least the algorithms here, in principle, they give you global optima, they give you upper lower bound on how close you are at the optimum. So at least for the range of problems that we considered here, LP, QP, MILP, MIQP, the standard algorithms give us at least upper lower bound anywhere in the search. So there's no need to go to some other tools. Okay. In terms of the nonlinear problems, or let's say not general nonlinear polynomial problems, for example, as a special case, people have looked at this. We have not. All right. But for example, Professor Fludas at Princeton University, as one example, has looked at the application of those global techniques. However, the question here is often, for those applications, do you really care about the global optimum? Okay, because very often what you want is there's a certain bound that you need to satisfy for stabilization. What's important is you satisfy those bounds such that at least stability is guaranteed. Global optimal, not that significant. In those cases, other examples, I'm sure it could be different.
So Manfred, I have to put you on the spot, you know?
Sure.
So who's going to win in November? No, that's not my question. But you said something a little, you know, that's actually sort of worrisome to me a little bit. You said that it wasn't any new technology, right? In the second part.
In that building.
Correct.
That, yeah.
Correct. And it's instruments like policy that are far more. I mean, if you say somebody doesn't turn off the lights, you charge them $50. Okay, that's going to change behavior. So my question is, what do you see as the role of technology in reducing new technology? Is it just like, is it a research problem?
Do you mean on the building side?
Yes.
Okay. I definitely see it that way. When I was talking about the building in Switzerland, okay, I said before in the introduction, this is not easily replicated. Okay, so this is, you know, this is not something you can say, okay, we have this building design, so why don't we use it everywhere? Okay, this is a one-of-a-kind design, okay, where there was a lot of effort and manpower and clever people that put this together, ideas specifically to this situation, the combination to reach that, to achieve that systems effect and to achieve those savings, okay? But I think when you take this group of people and say, okay, now write to me a book on how to do it, I don't think they could do it, okay? So I think to do that at scale, okay, I look at this as some glass ceiling, okay, that is broken through in the sense that you say, it is possible. See, it is possible. Let's strive to make this happen, both in terms of technology that you can apply at scale and the organizational political process that is necessary to realize that. I think that's the value of that building. Just like you may know, Lino Guzzella at ETH had this car and the world record in gasoline mileage, okay, which is an absurd number, okay, which, I don't know, 2,000 miles a gallon or something. It has no meaning in the sense of you're not going to buy this car, you can't drive it, but it tells you a little bit about what is possible. Okay, what is, and that goal is far out. So, for example, the improvements that we have, potential improvements, are a lot. And I think that building serves that purpose. It is not that it can say technology developed, we applied. Okay, I think, and so that's I think what is to be said about your question.
I will have a question.
Thank you, Francesco. Thank you.
Next speaker is going to be Eric Ferron from Georgia Tech. Same time, same room.
Not the regular.